Hello there, Energy 301 students. Dr. John Schrage here, and I'm going to show you a few more techniques that you're going to be using in Octave really throughout the semester, but especially in Project 1. There may be a handful of things that we're going to be doing that, they're just basic programming techniques. Honestly, it's very similar things are used in any programming language, whether a compiled language like C or whether an interpreted language like Octave. The syntax, the exact words and exactly how you use them will vary from language to language, but the idea will be the same. And one common technique that is used in really any programming language is about adding things up. Often you need to take a number and add another number to it, increasing the value of the first variable. Let me show you what I mean. Mathematically, this is actually impossible. Notice that you have I equals I plus 1. You're going to see lines like that all over the place in your Octave program here. I equals I plus 1, you can't, in a math class, ever resolve. There's no value of I for which that works, but yet lines like this happen all the time in computer programs. And that's because you need to think through how this is going to be evaluated on the computer. I mean, in a programming language, what's going to happen on an equation like this is it's going to evaluate the right-hand side of the equation. It's going to come up with a number that is how big that value is, and then it's just going to change the value on the left-hand side to match that. So whatever value is in I, let's say the value of I is 1,000. The right-hand side of the equation is then 1,000 plus 1, or 1,001, and then it will set the left-hand side equal to that, so I becomes 1,001. This is a way of incrementing the value of I by 1. This is actually a technique that you'll see all over the place in computer programs. Typically, it's necessary to put some kind of starting value into that value of I, that variable of I first, like set I equal to 0. For example, maybe you are counting the number of weather stations that you have available to you, as you read through a file or something like that. So maybe n will be the number of stations. So you will set n equal to 0, and as you read through each weather station, you'll increase n by 1, and when you're done reading the whole file, n it tells you how many weather stations there were. A very common strategy. Another common application of something where you're adding up like this would be if you're trying to compute an average, where you are adding up all of the elements that go into that average, and then you are computing the average by dividing by how many elements there were. So in this little example here, I'm computing a variable that I'm calling the sum of the temperatures in Fahrenheit. Okay, we're going to compute the average temperature in Fahrenheit. And I'm saying, if I start off with my sum T underscore F, my sum of my temperature in Fahrenheit, to use the practice that I want you to get into, I'm going to start off by setting it equal to 0, and then I'm saying the sum of the temperature in Fahrenheit equals the sum of the temperature in Fahrenheit plus the temperature in Omaha. And then I take that same number and I'm also adding the temperature in Lincoln. Now, you wouldn't really do it this way for just 2 stations, but I mean, if you had a long list of stations, this would be a strategy. Maybe you could be doing it inside of a loop, to use something that we'll be using in a little bit. And then I took the average temperature in Fahrenheit, which is just the sum divided by 2. In this particular case, you could have done it easier in Octave. You wouldn't have to start off by setting the value of the temperature in Fahrenheit to the sum of the temperatures in Fahrenheit to 0. You could have started off by having the first value just equal to Omaha and then add the value in Lincoln to it. That would have been a possibility, and you could have even done it more easily in Octave, but that would involve more techniques that we'll be learning later in the semester when we get more explicitly into statistics. I was just trying to show you this idea, though, of adding up values, since that mathematically the equation doesn't necessarily make that much sense. All right, let's talk about loops. Loops in Octave. Loops are a way to get a piece of code, a little part of your algorithm, to happen a multiple number of times, potentially a very large number of times. There are different types of loops in any programming language. All programming languages, though, broadly have 2 types of loops. One that executes a predetermined number of times. That's called a for loop. I don't know where the terminology for comes from in this context, but for loops happen a certain number of times. It's going to happen for so many times. Maybe that's where it comes from. That's in contrast to a while loop. We don't have any while loops coming up anytime soon in Octave, so I'm not going to teach you about that right now. But a while loop happens until something is true. While this is true, keep doing this. Okay? A for loop, though, is more commonly what we're going to be using in these kind of applications, where we're saying, oh, for each of the hours in this calculation, do this, or for each station, do this, or whatever. It's going to be a predetermined number of times. Now, that number of times might be from 1 to 100, or that might be n times, where n was how many weather stations there were, or something like that. But it's a number of times. when you get to the for loop, you know in advance how many times this code is going to happen. You might know it literally as in it's going to happen 100 times, or you might know it more symbolically, like you know it's going to happen n times, and you don't know yet what the value, I mean, you don't have a preconceived idea of how big n is, but you can do it, a for loop will happen a specific number of times. And the syntax of a for loop in Octave is different than it is in other languages, but the basic idea is the same. Here we have a loop control variable, I, and we are saying that this is the variable that's going to be keeping track of how many times this loop has happened. Now, you don't have to call it I, although traditionally loop control variables are usually IJK, okay? But they wouldn't have to be, but we typically do. So I, in this case, where for I is going to be going from 1 to 10. Then inside of that loop, between the for and the end for, there'll be stuff. I mean, right now I just have a comment there that says stuff happens there. But stuff will happen. And then we will repeat that loop, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. We're stepping by 1, because there's no loop interval there. We are assuming it's 1, so we're going from 1 to 10, and stuff will happen. Here we have a loop control variable that goes from 1 to 10 in steps of 0.1, and then each time something happens. Let's actually write a little program to do something like this. I'm going to just make a little, we're using Nano. I'm just going to make a little example of this. Let's call this example1.math. Alright, so here's my little program here. Let's actually just do a little example here. About for I equals 1 to 10, something is going to happen. And then that's the end of the loop here. So what should we have happen there? How about we just display the value in I? That seems easy enough. Here's a simple little loop. What's going to happen is this little loop here will happen. Let me use my mouse to illustrate here. This little loop here will happen 10 times. It'll happen when I is equal to 1, I is equal to 2, I is equal to 3, and so on. So I'm going to go ahead and save and leave. And then I'm going to get into Octave, like this. And I'm going to say run example1.mat. And look what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All we did is display the values in that variable 10 times. I'm going to go ahead and get out of MATLAB, and I'm going to go over here and bring back up example1.matlab again. Actually, it's out of Octave, of course. What if we said we'll go from 1 to 10 in steps of 0.1? So now that loop control variable will start off equal to 1, and then it will increase to 1.01, and then 1.02, and so on, all the way up until the value of 10. Each time it'll display the value of I. Let's get out of this and see if it works. Octave, run example1.mat. Look. Oh, okay, so it started off at 1, and it's good. Okay, now it's only showing us one screen full of these values here. You can go forward, forward, forward as you work your way through and see all the values that it's displaying to the screen, or you can just sort of quit and get back to your Octave prompt, and that's fine. We could have, let's go ahead and quit or exit this again, and I'm going to go back into Nano. And we could do more than just display here. I mean, we could have done anything over here. We could say display the sign. I mean, we could do some calculations here. Let's just say f equals the sine of I times pi. Yeah, whatever. That seems fine. Display f. Okay. Now, that many times we'll be displaying the value of f, where f is I times the sine of, the sine of I times pi. Just to show that we could do something else here, after this, let's just say, let's just do another calculation. Let's just say x equals 2 times pi, just to do something here. Display x. Alright, just to see something here. Notice, by the way, I'm being sloppy about semicolons. I don't know. Let's try it. Let's see if it works. Control exit. There we go. There we go. There we go. Let's go back into Octave and say run example1.mat. Whee! Okay, so here we are. We're displaying f is equal to this, f is equal to that. You see how we're getting the sine of all of this here, and whatever. displaying, 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 and at some point we would actually hit all the way down there at the bottom of the program where x was equal to 2 pi, but I don't see that one coming up just yet. Anyway, it would go all the way though down to the end. There we go. X equals 2. Remember, so here's all of our inside the loop. These things happened, whatever that would work out to, 1,000 times or whatever. And this is the one time that it displayed the value of x. All right. Let me show you a couple little tricks that I've been doing here along the way. Actually, just so you can see what's going on here. Once you are back to the Linux command line, one of the tricks you could do rather than sit there and retyping each time that you want to go into nano of example 1 or whatever, I mean that's kind of error prone, you can misspell it or whatever. The up button on your keyboard scrolls you through commands you have recently used. So like if I just hit the up button twice, I'm now back to, it's saying, you mean nano example 1.mat, right? Yes, I do. Just go ahead and enter and you're fine. Okay, that's a nice trick. Oops, sorry. Same with like, now I'm back at the command prompt. Okay, I want to run Octave. Alright, I can just hit the up button twice and it'll be running Octave for me. Okay, I just hit enter to say, yes, that's the one I meant. Alright, so that's pretty straightforward as to what those little tricks are. Let's do another example here that's on your PowerPoint. It says for x is equal to 1 to 100. See how we've declared an array here? Here, let me make an example 2. We'll actually make this one. Okay, x equals 1 to 100. Y is equal to x. Alright, let's actually walk through here. What's going to happen here? I'm first of all creating an array that goes from 1 to 100. Heavens, let's actually do this. Let's do this step by step. I'm saving this. Okay, let's go back into Octave and run example2.mat. Alright, so now see how x is equal to, and then it's showing us the 100 columns of the array that is x, where they go from 1 to 100. Okay, you can see how that worked. Oops, there we go. Alright, go back into nano. Alright. Now what we're actually going to be doing is we're going to be creating an array called y, and y, each element of y is going to be equal to the same corresponding value of x just times pi, just to do some calculation. Now, in order to do that we have to have an array called y, and it needs to be the same dimension, the same rank as x. It needs to have the same number of rows and columns. And the easiest trick to do that is just to say y is equal to x. Y is not going to be equal to x. Y is going to be equal to the values in x times pi, but this will force it to make the same number of rows and columns in y as there are in x. Then we'll just replace all the values in y with something else. So for example, since we know that there are 100 values in there, we're going to go for I equals 1 to 100. And 4. What's going to happen? Well, we're going to take each value of y, and we're going to take each value of x and multiply that x value by pi. Alright, and so the value x1 will be multiplied by pi and put into y1. The value x2 will be multiplied by pi and put into y2, and so on, all the way through here. Let's go ahead and run this little program. Control X, save buffer, yes, write it. Go back into Octave and say run example2.mat. And okay, here's all our values of x, and now here's our values of y. What happened here? Oh, I know why. Okay, but if I actually display the values of y, you now see that y is equal to x times pi. What actually happened here? Let me go back. That's actually an interesting question. Y is supposed to be x times pi. How come? There, let's go back into Octave. Run example2.mat. Okay, I see x is equal. Let me use my mouse here. X is equal to. Oops, that's not good. X is equal to, and then here's all my values. X is equal to 1, x is equal to 2, etc. Alright, forward. Now, y is equal to, well, shouldn't this all be pi times 1, pi times 2, pi times 3? It's not. Oh, well, I know why. Let's go back and look at our program. See, what we were still seeing was this line. Y was being set equal to x. Originally, they match each other. Then, we're saying, oh, I see, this, and this. I'm just curious as to why we're always seeing this on the screen. I wonder if that's what the semicolon is. Let's put some semicolons here and test that. Save modified buffer, yes. Octave, run example2.mat. That is the difference. I just discovered something live on video. That's the difference between semicolons and not semicolons. If we put the semicolon here, it won't actually display the values of x, it's just doing the calculation. It won't display the values of y, it'll just do the calculation. So now if I like added a line here that said display y, it'll have computed the values of x. X is just an array that holds the numbers from 1 to 100. Originally y was just the same thing as x, but then we went through from 1 to 100 and replaced those values of y with x times pi. Now I understand. I have been wondering about that about Octave for years. Okay, so if we go back into Octave now and we say run example2.mat, look at this, we are just getting the values of y, where they are the values of x times pi. Now I understand. Okay, cool. It's always important to learn these things here. Now, the reality is in Octave we could have done the same calculation much more easily. Because you don't actually need to do these calculations one element of an array at a time. We could have just taken the matrix x and multiplied it by the constant pi, and it would have worked just fine. That's one of the brilliant things about MATLAB, is that would have worked just fine. Now, as long as when you create an array, you know in advance. I mean, when I created this array, let's go back into here, I knew that it had 100 elements. It went from 1 to 100. So I could go from 1 to 100, and I knew I would be doing this for every one of the 100 values in x. But that isn't always the case. Sometimes you don't know. I mean, like in this example here in the red box here, I know that there are 5 values in x. If I'm going to do some calculation on each of those values in x, I know there's 5 of them. That's not so problematic. So like a little loop like this one right here that I'm just showing you in the little blue box or whatever, I mean, if I did some calculation, I just wanted to increase the value of x in each of those elements by 1, I could just do a loop from I equals 1 to 5, and for then each of those values, x1 is equal to x1 plus 1, x2 is equal to x2 plus 2, and this would just add. That's easy. On the other hand, sometimes you don't know right off the top of your head how many that would be. I mean, like, look at this one in the red box here. If I had some array t that goes from 0 to 2 pi in steps of 0.05, okay, so it's going to have a value in it like 0, 0.05, 0.10, 0.15, etc., all the way up to 2 pi, which is, what, 6.28, whatever. Yeah, I can count on my fingers or do the math or whatever and figure out how many that is, but, you know, off the top of my head, I don't know. I don't know how many rows are there, or how many columns, rather, are there in this t array. That's a very common problem. So, I mean, like, if I wanted to take these values of t and do something like increase them each by 1, like in this little blue box that's right here, I see I need to do it, I'm going to say it n times. The problem is I don't know it. I don't know what n will be. I need some way of finding out how many columns are in my array. So then I could just say, okay, then for that many times, let me do some calculation on t of I. Alright? Well, it turns out there's a nifty little command in Octave that will tell you how many columns there are. It's columns. And then in parentheses, you're going to put the name of the array that you want to know how many columns there are. So, like, see in my example there, I've added a command, columns, n equals columns t. So, like, if I had a, you know, higher up in the program than what I'm showing there in that blue box, if higher up in that program I had said t is equal to, you know, what was it, 0 to 2 pi in steps of 0.01, n is now equal to the number of columns that are in there. I'll do an example in just a moment here. So then my loop can be for I equals 1 to n, because now I know n is the number of columns that are in that array. Let's actually do a little example like that. I'm going to go ahead and save this, and I'm going to say, let's make a new example here. Example 3.mat. Alright, so let's just make some tricky array. How about t equals 0 to, let's say 2 pi, what the heck? 2 times pi. And it's going to go in steps of, let's just use some weird number. For some reason, we're going to go in steps of 0.017. I don't care, whatever. I don't actually know how many rows and columns that is. And if I wanted to do something to each of those rows and columns of t, you know, for example, maybe f is going to be equal to t of I times, let's just say the tangent. It's going to be equal to the tangent of t of I. Okay, I don't know why you would do that. Maybe you're plotting something or whatever. Okay, so this is just some silly little calculation here. We're just computing a scalar constant, well, a scalar variable f. It's just equal to the tangent of t of I. Whatever. Okay, this would work here. except I don't know how many values of t there are. So, for example, I could say this n is equal to the number of columns in t. Okay? I don't know what it is, but it's some number. You know, 105 or something. I don't know exactly what the number's going to be. And then for each of these times, from I equals 1 to n, that value, that column of the t array, t1, t2, all the way up to tn, we're saying take the tangent of that and put that value into f. And Evans, just to give this program something that'll do on the screen, let's just display the value of f. Yes. Okay, let's try that. Save it. Yes. Okay. Octave. Run example3.map. Okay, these are the tangents of all those values here. Okay, which is fine. I don't know anything about what's all going on here, but whatever. That's the values of the tangent of t, where t goes from 0 to 2 pi. Cool. All right. I mean, you can see on this example here that I have on the blue box there. I mean, look in the red box first. What if I had an array that, you know, I don't even know the beginning, I don't know the step, and I don't know the end. This array z is going to go from some number alpha, which I presumably computed higher up in the program, to some number gamma, which is presumably farther up in the program if we set a value to gamma. And we're going in steps beta, which are, you know, something, again, we probably computed higher up in the program. I mean, I have no way in advance of knowing how many elements are in this array. Well, that's not entirely true. It would not be simple to count to determine how many elements there'll be in that array. But you know what will work? Columns. The columns command. N equals columns of z will work. Okay? It'll just tell you how many columns that array has. A very, very slick trick commonly used in loops. Let me show you another common thing that we do in loops. We nest them. We put one loop inside of another. This is a particularly useful tool for, like, when you're working with grids of data, like an array that has both rows and columns. This can be useful when you're talking about, like, you know, for every day, in, you know, like, let's say you're doing this calculation, well, here, this example that I have here in the blue box. You're going to be doing calculations very much like this in Project 1, where you're going to say, I'm going to be doing some calculations for every day of the year and at every hour of the day. So, like, for every day from 1, 2, 3, all the way up to 365, and for every hour, for that day, every hour of the day, we're going to do some calculation in there. So, again, let's make a little example here. What would that be? Example 4. Let's make nano example 4. Alright, let's just do something very, very simple here. For day, let's just say day equals 1 to 365. Hey, let me give you some programming techniques. Generally speaking, when I start a for statement, I go ahead right away and put the end for that matches up to it. Because if you don't have as many fors and end fors, you're going to get an error. Okay? Secondly, here's another, so I mean, you can always go back up then and put the stuff that goes in between. Secondly, the stuff inside the loop, you usually indent a few spaces over. Okay, so like inside of here, let's say I'll have for hour equals 1 to 24. And again, right off the bat, I'm going to put in end for so that I know these match up. Okay, and what do we want to do here? For now, let's just say we're going to put in here, what are we going to put in here? Let's just say we're going to put, we're going to make a variable called hours since New Year's equals day minus 1 times 24 plus hour. Okay, so like for example, that would be how many hours it's been since New Year's Day. Since New Year's Eve or whatever. So like you take the day minus 1, because on January 1st it's been 0 days since, times 24 plus the number of hours. Okay, that's just a silly, simple little calculation here. Let's just go ahead and save that modified buffer, run Octave, and say run example4.map. Hours since New Year's equals 1, 2, 3, 4. It's going to go all the way through 365 days of the year, 24 hours on each day, and I don't know how far, what will this take? Oh my, this is going to take a long time, because, yeah, how many hours are there in a year? Woo, it's just going to go and go and go. I don't know how far that will go. I'll hit quit. Cool. Alright. Before we move forward to learn another technique, I want you to get a little bit of practice writing an Octave program. So for question 1 on this little assignment here, I want you to write a little program that is going to add all of the integers from 1 to 10,000. and then answer this question as to what is the sum of all the integers from 1 to 10,000. Okay, I tried this little example before I started recording this video, and I think it took me either 4 or 5 lines of MATLAB. I mean, basically I'm going to make some little variable I'm going to call like sum or something like that, set it equal to 0, and then I'm going to make a little loop that goes from 1 to 10,000, each time adding that value of I or whatever to the value of the sum. So each time inside of there I'm going to say sum equals sum plus the value of that, 1, 2, 3, 4, 5, all the way up. So what is the sum of the numbers from 1 to 10,000? See if you can throw together a quick little 4 or 5 line of Octave program and compute the calculation and see if you get the right answer. Then click on the answer in the links below this video, and it'll help you know if you're right or you're wrong before we move on to part 2 of this lecture.